This is dual active DC to DC converter. Here there are two methods to step up the voltage. One is a normal boost converter operation. Here when this switch is on, the inductor will be charged, and when the switch is off, the inductor is discharging, gets added with the input voltage and boost up the output voltage, load voltage. This is one thing. And another thing is we are using a step-up transformer, high frequency step-up transformer. Here the boost converter operation, it will step up the voltage from 24 volt to 80 volt. From this, the transformer steps up the voltage from 80 to 400 volt. So this is stepping up the voltage using two techniques. Here the input voltage initially we are providing as 12 volt, and after 0.5 seconds 24 volt will be provided as input. And here we are adding additional switches in order to maintain the continuous conduction mode. Here if you see means when the switch is on, at the time the inductor will be charged and the input will be cut off from the output. At the time during that period, here this capacitor will discharge and provide energy to the transformer with this inductor. So the transformer will provide the output to the secondary part, that is the voltage at the load side. Here the capacitors will be charging those inductor, and at primary side the current will be flowing. Hence in the secondary side we will get the output voltage, that is the EMF, that is provided to the rectifier here. Similarly for this particular setup and this capacitors, this transformer is used. So we are stepping up even when the main inductor is charging, and when it is discharging, the current will flow through this inductor and it will provide the energy to the transformer, and EMF will be induced in the secondary part. At the time the capacitor will be charged. Here we have providing one PI controller based voltage control loop. The output voltage is taken as feedback and provided to the control loop, and reference voltage is 400 volt. And both are compared, and error is given to the per unit conversion. We are converting the error voltage into per unit, that is in terms of -1 to +1, and it is given to PI controller. The PI controller will generate the duty ratio depending upon the error voltage, and the duty ratio will be provided for pulse generation, and the pulse generated will be given to the MOSFETs. Also, if you see here, this is the MOSFET, main MOSFET voltage and pulses. First one is pulse, gate pulse. Second one is voltage. Third one is current. When the pulse is on, the MOSFET conducts, so voltage will be 0 and current is around 40 amps. And when the pulse is 0, that means MOSFET is off. At the time the voltage is increased, and here it is nearly 80 volt we are getting. That is how much it is stepping up. That much voltage only we will get across the MOSFET. So compared to the load voltage, here the MOSFET voltage is very less due to the usage of this high frequency transformers. Because the primary side voltage is 80 volt only, so the MOSFET is maintaining the 80 volt here. By doing this, we can reduce the voltage stress across the MOSFET, so that losses also will be very less in this. Also, one more thing. Here these are auxiliary switches. In auxiliary switches, if you see means same voltage is same 80 volt only. Current is around 25 amps, 20 amps, 25 amps. And here if you see means we are achieving zero voltage switching and zero current switching. Here, usually when the MOSFET is off, the voltage across the MOSFET will be increased. And when until the voltage will be maintained until the MOSFET is turned on again during the next cycle. But here, before the MOSFET is turned on in next cycle, the voltage reached zero. This is zero voltage switching. This is caused by the conduction of the body diode. Here, if you see means the current is negative, MOSFET current is negative. That means the anti-parallel diode, that is body diode of the MOSFET is conducting, so that voltage reached zero here. This is zero voltage switching. And zero for zero current switching, here the MOSFET is on. At this point, the MOSFET is on. Okay. So the MOSFET will conduct until it is turned off. But here, if you see means the MOSFET current, it is going below zero before the MOSFET is turned off. Okay. During halfway time period, the MOSFET stops conducting and the diode starts conducting. So when the MOSFET is turned off, the MOSFET current is zero. So this is zero current switching. Why this is essential means, while calculating the losses, we need the switch on losses and switch off losses. While MOSFET is turned on, what is the voltage and current? Depending upon that, losses will be calculated. And for switch off loss, when the MOSFET is turned off, what is the voltage and current? Based on that, losses are calculated. But here, if it is zero voltage switching and zero current switching is achieved, the losses will be very less, nearly to zero. So when the losses is reduced, switch on losses and switch off losses are minimized almost zero, then the switch, that is switching losses, will be very, very less. When the switching losses are reduced, then we can increase to any frequency, and then the losses will be not increased or decreased. It will not be changed. Losses will be very, very less. In power electronics circuit, the switching losses is of main concern. When those losses are itself, it is very minimum, then the efficiency will be very high. The other losses we can consider as inductor core loss and this diode switching losses and all. That and all very minimum only conduction losses will be there. And this is the efficiency. As I said, due to the zero current switching and zero voltage switching, losses are minimized. And here the efficiency, it is reaching nearly 95%, 95 to 96%. First one is efficiency curve. Second one is load power, 200 watts. Third one is input power. That is also nearly 200 watts. Is nearly 210 watts, 205 watts we are getting. That is the input power. Output power is 200 watts. And this is the step up. That is, first one is input voltage. Initially it is around 12 volt. And after 0.5 seconds, the input is increased to 24 volt. And here we are getting the output voltage 400 at both conditions. Due to the closed loop control, that is voltage control loop. Here initially when the input is 12 volt, the output is around 394 volt. Okay. When the input is 24 volt, the output is around 399 volt. So we are maintaining the same load voltage even when the input changes. That is twice the amount of voltage is increased. And this is the main inductor current. That is when the switch is on, the inductor will be charging. So the inductor current is increasing. When the switch is off, the inductor will be discharging. So the inductor current is reducing here. The charging and discharging of the inductor is provided in this graphs. So we can able to step up the voltage from 12 volt to 400 volt without having much voltage stress across the switches. And also we are achieving zero voltage switching and zero current switching. So the losses will be very less and improves the efficiency. And by using the voltage control loop, we can able to regulate the load voltage irrespective of the changes in the input voltage.